today's topic. Um, let's take it from the very top of what high-speed LANs is. Generally, high-speed LAN is considered transmissions that are of comparatively higher rate transmission. We're talking about 10 meg, 100 meg, 1 gig, 10 gig and up. Those are what we generally consider high-speed LANs. The IEEE 102.3 standard, which generally deals with Ethernet, happens to encompass data rates that are within those 10, 100, and 1 gig and then a 10 gig transmission. Those, in a way, considered high-speed LANs, as I pointed out earlier. But today, if we really talk about high-speed LANs, I wouldn't really factor 100 meg into it, even though it's part of the standard. Because we look at transmission that are very, very significant in its application in terms of fast transmission, get information from one end to another at a much faster rate, you know. But in a way, technically, yeah, 10 meg will factor into that aspect. So we want to look at some of these high-speed connections and how they build, structured, how they work, some of the challenges that goes with it, issues, how they were resolved, and what have you. So we'll look at a number of things, how far it's come over the years, with respect to various standards and technologies. So it's supposed to be a really good concept, since a number of today's transmission are within higher transmission. Today we're looking for information that is the speed that can come at the speed of light. Nobody wants to sit back and wait for minutes or even more than 5 seconds to get a particular request sent back to them or executed. So we're looking at ways to make information transmission much more faster. And that's where high-speed LANs come into play. Within the objectives, let's see what we're going to be looking at. So some of the key objectives, obviously fundamentals is always important of high-speed LANs, starting from Ethernet point of view. As I mentioned earlier, Ethernet happens to be the IEEE 802.3 standard, which encompasses data rates that are 10 meg up to and up. 10 meg and up, 10 meg, 100 meg, 1 gig, 10 gig and up, so they all encompass within that type of transmission standard, which is known as Ethernet. We'll look at some of the earlier standards for high-speed transmission. From Aloha to your carrier sense multiple access with collision detection as a way to resolve some of these challenges. So these are more or less your earlier implementation of high-speed LANs, and challenges came up within them got resolved with the different standards or different designs that came up. So Aloha was the initial one, and it had so many challenges, so they moved on to a better standard or a better implementation called Aloha to basically address some of the challenges that Aloha had. And then even with the slotted aloha, obviously were challenged as well, so they came up with these CSMA slash collision detection or carrier sense multiple access collision detection. Obviously, you could tell from the acronym of this that these two probably had issues with collision or sensing multiple connection or multiple signal on a given transmission medium. And to avoid collision, they had to implement the CSMAs to solve that. So it tells you that these two actually had issues with collisions and sensing of a signal in a particular medium. And then we also look at Ethernet examples, which are, as I pointed out, from 10 meg all the way up to 100 gig per second. The applications and some implementations that goes with Ethernet as a preference. Okay, so fundamentals, most widely used high-speed LANs include Ethernet. Ethernet happens to be the most easiest standard, well implemented to address high-speed LAN transmission. We also do have fiber channels as well as wireless LAN, high-speed wireless LANs, which today it's all over the place. You got your 4Gs, your 5Gs, and now they are addressing higher transmission rate. In general, but it's mostly start with Ethernet, which happens to be the base of the IEEE 802.3 standard to help with transmission rates that are of the higher rates increment from 10 meg all the way up to 10 gig and even up today. So generally, Ethernet was designed to address a number of key issues. Okay, they were mostly used for packet switch LAN technology with bandwidth that ranges within the 10 meg, to even 10 gigahertz or gigabits per second. They had a maximum bus length in terms of how far they can go in distance before they introduce a repeater. Was actually 500 meters per segment and repeated every 500 meters. Okay, so in general, so in all, maximum bus length of an Ethernet frame would be 2,500 or 2,500 meters. That's about the length it can take before the signal kind of like dwindles, becomes much more considered useless. But within the segments of that 2,500 meters or bus of maximum bus length, we do have segmentation of 500 meters. So every 500 meters, a repeater needs to be introduced to boost up the signal for another 500 meters. So if you think about 4 repeaters of 500 meters, that should give you 2,000. So give and take, we have a maximum of 2,500 meters, which is about right. So you could go as far as that. You can push the 5 segments or 5 repeaters, but generally, to get the most, ideally, within 500 meter segments, you need 4 repeaters to accomplish your the maximum bus length or the ideal bus length. Okay. Most of the topologies used for connecting Ethernet transmissions were bus and star topology. If you remember bus topology very carefully, you use one lane or one bus lane to interconnect various other devices or host devices. Whereas the star topology, you use a central node to interconnect um, various nodes or various host devices, like a switch with a central device where every other node connects to. Whereas the bus was just one channel link or transmission medium where other devices interconnected. So there was no switching on that particular bus link. But they had ways of addressing, collision and other stuff within that. Okay. We'll go back to fiber channels and high-speed LANs, but Ethernet is the most focused one. It's widely focused one on the high-speed LANs. Connections made to hosts via some type of transmission medium, which could be either twisted pair. So we're looking at the medium that's used to carry some of these high-speed LANs standards. So we have twisted pair fiber optics or radio waves, So that's what's going over within Ethernet, mostly used as a packet switch LAN technology. And bandwidth were obviously 10 meg all the way up to 10 gigabits per second. And as we also mentioned earlier on, the maximum bus length on Ethernet was 2,500 meters. That's the maximum you can go before the signal itself loses its strength. And within that 2,500, there are segments of 500 meters, which can be repeated 4 times. Obviously within 2,500 meters, you can repeat it for 5 times, right? But to get the optimal, transmission, ideally it's in segments of 500 meters. So after every 500 meters, you want to introduce of an Ethernet frame. Ideally, you should introduce a repeater. And I wouldn't apply. I would. This also quite dependent on a transmission medium you're using. Obviously, if you were using a twisted pair or a coaxial cable, copper cable in general, if you remember correctly from data communication 1, you'd have 100 meters as the maximum transmission length for most of your copper cables, from twisted pair to coaxial cables or copper cables in general. They go up to 100 meters before you introduce, and then they require a repeater to be introduced. So you have to keep that in mind. If you want to accomplish 500 meters, then you're probably not going to be using a copper cable. Ideally, you probably go for fiber optics. Okay, so keep that in mind. And since we're talking about more or less higher speed transmission or high speed LAN, obviously fiber optic will play a key role over here. So hence the 500 meter segments with 4 repeaters introduction. Okay, and as I was also pointing out, topologies that are used revolves around bus and that topology. So this will explain, how some of these topologies actually work. Your hosts were attached to network via Ethernet transceivers, either through a hub or switch, and they detect line states and send as well as receive signal as and when they come true. Hubs are used to facilitate shared connections. So ideally, they're not very efficient in terms of handling transmission needs at a higher rate of many interconnected nodes. Hence the reason why it was switched it was actually move to a switch level instead of a hub. And considering the broadcast domain that hubs have, if you were to deal with a high volume of nodes on a particular topology, they wouldn't be very efficient in handling your broadcast domain. But anyway, they form part of your uh, host connection to either of these topologies. All hosts on an Ethernet are competing for access to a particular medium. Yes, obviously, we're all fighting for. It's like having one road, or let me say one lane road, and packing a whole bunch of cars on it. Obviously, there's going to be issues. We're going to be competing for access. As you would see on the roads, if there's a traffic on our roads, you notice that it gets pretty jam packed. People are always competing. People are trying to get through traffic here and there by any means possible. So there's that contention, going on uh, when it comes to Ethernet. So there has to be ways to address some of these, contention to make sure uh, mediums are efficiently used, and that's where switch comes into play. Like I said, as I was mentioning earlier on, hubs had a really terrible way of handling shared connection. So switch were used to break that model to help make sharing of medium a lot more efficient and effective in terms of transmission. Ethernet, by definition, is actually a broadcast protocol under the IEEE 802.3 standard, which deals with any signals that can be received by every other host or all other hosts on a particular network. And switching enables individual hosts to handle the communication back and forth. So in terms of how Ethernet handles its broadcast protocol, switching does a pretty good job of making sure things were much individually coordinated. You know, at the network layer is where obviously packets are received from the Ethernet at the data link layer. Obviously, Ethernet falls under the data link layer, which is layer 2. Um, and it has a frame format, just like any other transmission protocol standard. It would have its own frame format for identifying how informations are carried on the Ethernet standard. So we'll look at some of those very soon, so at least you can identify them. Okay, so yeah, we have frame formats with the and they all have allocated number of bits, just like we did for ATMs and what have you. With frame formats, keep in mind Ethernet is a layer 2 standard, protocol standard, so it deals with frames. Okay, and at layer 3 we have packets. So at the Ethernet layer, where frames are more of the key level of signals, there are quite a number of implemented bits categorization for the format of frame that gets carried across the Ethernet protocol. The first of the format within its segmentations is the preamble, which carries 64 bits. Generally, preambles, so it's either 64 bits or 4 bytes, because byte is 8 bits. So if you divide 64 by 8, you have 8 bytes. Okay, if you divide 64 bits by 8, you'd have 8 bytes. So generally, the preamble was designed as a segment to handle with two communication interfaces synchronization. So when we talk about how signals are synchronized at the Ethernet interface, it's the job of the preamble field to identify how signals are going to be synchronized between two separate interfaces that wants to exchange information. Destination address, which is the next in line within the fields of segmentation of an Ethernet frame format, carried 48 bits or 6 bytes, and destination address, obviously, as you know, is where the recipient is destined for, or where frame destination is destined to, or it's going to where frame is going to. Basically, is the destination address. Source will be uh, the where the frame is originating from, hence the source, and destination will be the recipient. So all these two are also handled within the frame format, and they both carry 48 bits each, or 6 bytes. When it comes to the type, which is 16 bits or 2 bytes, they generally designed to identify the type of data being carried, uh, especially at the operating system level. So for instance, if you're talking about a Windows machine sending a frame to another Windows machine, it's the job of the frame type to determine how the operating system, the two operating systems of Windows type, should handle the transmission or process. If it's a different operating system, like for instance Windows 2 and Mac OS, the same job of the frame type to be able to identify the smooth transition of, of, of how the information is going to be negotiated between the two operating systems. You need to understand that two different operating systems they have their own way of transmitting information. So ideally, there has to be a way, since they are both using Ethernet as a standard, there has to be a way for them to identify uh, how they want to transmit the information at that particular level. So they obviously came up with that, knowing very well we do have a number of operating systems. Uh, Frame types were built to or were segmented to address some of these issues. So their job was to identify the types of data being carried on the various operating system modules to determine how processes are going to be done within the frame transmission. And then the body, which consists of the largest part, is where the actual data is carried. The frame data part, which is the body, consists of, it goes from 1200 all the way up to 1500. Or should I say it actually starts from 368 bits or 48 bytes, which could be which could be 12,000 bits or 1500 bytes. I'm just dividing in my head by 8, looking at the number of bits involved. So at the low end, you have 368 bits or 46 bytes, and at the high end, you'd have 12,000 bits. So if you notice over here, it's within states There wasn't a specific number of bits stated to define it evenly because they have a high and low um, limitation for the bits that the data can consist of. And keep in mind, we're talking about high speed lines away. So we're looking at big, data, huge amount of data. So we can't really fix a particular number of bits for it. But we do have a range. There is obviously a range um, to address the amount of data that can be carried in a body, which is your data or your frame data or data frame. And like I said, it's the minimum is 368 bits, and which is 46 bytes, if I'm not mistaken. And at the highest point, or at its maximum range, you have 12,000 bits, or 1,500 bytes. Okay, and that's what actually carries the actual data. Then you have 32 bits specifically allocated for your cyclic redundancy check, generally used for error controls, error detections, accuracy of data transmission or transmitted across your Ethernet transmission. So a number of key stuff within the Ethernet frame format. Okay, so these are some of this is actually where the Ethernet frames are, the various segments and their uh, data allocations. So as I was pointing with the data part, you have the minimum of 368 bits or 46 bytes up to 12,000 bits or 1,500 bytes. Okay, for Ethernet at the switching level, generally it just forwards filter frames based on LAN addresses. One question you're probably going to get in your CCNA class if you decide to switch, or go along the path of networks or being a network administrator or pure network engineer, one of the questions you're probably going to be asked in your CCNA or some of your networking certification courses will be at which level does Ethernet works in terms of forwarding of information that comes through. And that's where you indicate your layer 2, dealing with forwarding and filtering of frames within a LAN address. And the LAN address here would be your MAC address or your media access control addresses. Okay, so keep that in mind. At the switching level for Ethernet, it's purely frames forwarding and filtration. At a local area network address level, need to be very careful with that. We're not talking about IP address over here. We're talking about MAC address here within the LAN address of how switches at the Ethernet standard or protocol level handles the information, the frames that comes through. Since it's a layer 2 protocol, we don't talk about IP addresses here. And obviously, IP addresses are reserved for layer 3. And that also means they're reserved for information that are going out of a particular LAN. So keep that in mind. The very moment you want to move packet out of your LAN, then it ceases to be within the layer 2 level. It has to move to layer 3. And that's where your IP address comes into play. But for as long as you're moving frames within a given LAN, layer 2 is one of the most vital layer that you deal with. We don't deal with IP address. You just pure MAC addresses forwarding frames and filtering them out back and forth within that particular LAN. So it's kind of like when you have one switch which forms a particular LAN and you're forwarding messages, information, whether they are packets or frames or whatever it is.